Welcome! In this lecture we start analyzing the forces acting on a vehicle when it's driving, with the purpose to determine how much traction force the powertrain needs to produce. We start by analyzing the rolling resistance from the tires and the aerodynamic resistance, as they are always present when a vehicle is driving. Only the forces in the longitudinal direction will be analyzed, since they influence the powertrain. Forces in other directions are neglected, as they mainly influence the steering and suspension. When the vehicle is stationary on a flat road, there is no longitudinal forces acting on the vehicle. When the vehicle moves forward, the tires cause rolling resistance. All the wheels have rolling resistance, but for our analysis it is sufficient to only analyze the total rolling resistance force. We choose to illustrate the rolling resistance force only at the rear wheel in this picture. The rolling resistance is zero at standstill. When the speed is non-zero, it can be calculated as the rolling resistance coefficient multiplied with the normal force between the vehicle and the road. The normal force is vehicle mass times gravity times cosine for the road angle. The rolling resistance is approximately independent of speed, as shown in this diagram. It changes slightly with road angle, since the normal force decreases if the road becomes very steep. The rolling resistance is always opposing the driving direction, which means that it changes sign when the driving is in reverse direction. The rolling resistance coefficient should typically be as low as possible to keep energy consumption low, and it typically is only about 0.01. Once the vehicle moves a little faster, there is also aerodynamic resistance, which is caused by the air as it's forced to flow around the vehicle when it's driving. Aerodynamic forces occur all around the vehicle, but here we illustrate them as one concentrated force acting on the rear of the vehicle. The aerodynamic resistance mainly is caused by higher air pressure in front of the vehicle and lower pressure behind it. When the vehicle speed increases, more air has to pass the vehicle per second, leading to higher aerodynamic drag force. At a speed around 75 km per hour, the aerodynamic force is similar in size to the rolling resistance for a typical car. As the speed increases even further, the aerodynamic force increases more and more quickly. The aerodynamic resistance is zero at standstill. It can be calculated as the aerodynamic drag coefficient times the front area of the vehicle times the air density times the vehicle speed squared divided by 2. The drag force increases with the square of the vehicle speed, as is shown in this diagram. It is opposing the driving direction, and it is independent of the road angle and the vehicle mass. The aerodynamic drag coefficient should be as low as possible, and typically is about 0.25 to 0.35 for a modern car. For trucks and buses it is higher, about 0.7. In this lecture we have presented two forces which are always present when a vehicle is driving. It is rolling resistance, which is rather constant with the vehicle speed, and aerodynamic drag, which increases with the square of the speed. At low speed, rolling resistance is bigger than aerodynamic drag, and for a modern car, the aerodynamic resistance is bigger, above roughly 70 km per hour. Before we go on to analyze the force needed for acceleration, test what you have learned about rolling resistance and aerodynamic resistance in the following exercises. Thank you for watching.